Okay, hello. In this video, we're going to look at videos at PDEs that can be solved by direct integration. So yeah, there is PDEs that can be solved by direct integration or treating them as ODEs. We're going to look at two classes of PDEs that are amenable to these approaches. Okay, first of all, first order PDEs where the derivative term, there is only one derivative term, then these can be integrated as ODEs, so with only one derivative term. So these ones can be evaluated as ODEs, can be treated as first order ODEs. Then next we have got higher order ODEs, but these ones we need them to be linear. So higher order linear PDEs. So there are two classes here. First of all, it's PDEs that involve derivatives with respect to only one variable. These ones can be integrated directly again by treating them as ODEs. So these can be treated as ODEs. Then the higher order PDEs, which have factorable derivative operators, so here we factor out the operators and integrate directly. I think it's probably going to be best to demonstrate what we're talking about here through examples. All right, so let's look at some examples now. All right, so we're going to look at the following examples. In A, we have got ux equals to x sine y. So let's see how this works out. So ux 2x sine y. Okay, so I'm going to use the partial notation. So this is the situation we have. So here, if we simply take the partial x to the right hand side, and then now we can integrate both sides. Sine y partial x. So on the right hand side, we just have partial integral of the expression with respect to x. So it's just the reverse of partial differentiation, which means we consider everything else a constant except the x terms. So in fact we could factor out the sign from the integration. So on the left hand side we're going to have u, then on the right hand side this is going to integrate to x squared, so we're going to have x squared sine y. And then since we're integrating partially with respect to x, this is going to be plus an arbitrary function of y, and so that's going to be our general solution for A. In B we have ux plus 2u equal to x, so ux 2u is equals to x. When x equals to a half, u is e to the power y. Okay, so this one is a first order ODE, PDE, but there is only one derivative involved. Well, just like it was the case here, but this one there's only the derivative term, so that's why I can simply integrate. So this one we can treat it as an ODE. So if you like, we can treat it as y prime plus 2y is equal to x, which is a linear ODE. The integrating factor would be that one on account of this. So here we're going to do exactly the same thing. So if we multiply both sides by e to the 2x, the left hand side is going to be u e to the 2x is equals to xe to the 2x. And then if we integrate on both sides partially with respect to x, left hand side is going to give us u e to the 2x. This side is going to give us x e to the 2x dx. Now, so whenever we've got a polynomial times an exponential that we want to integrate, tabular integration is always going to be the method of choice. Tabular integration is an abridged version of integration by parts, but so you typically tabular integration works out much quicker than integration by parts. So whenever we have a polynomial times either an exponential or sine or cosine or hyperbolic sine or hyperbolic cosine, then we will always go for tabular integration. That's what we recommend you do as well. So this is going to be e to the 2x. Then on the right hand side we're going to have 1 over 4 2x minus 1 e to the 2x. Then this is going to be some function of y because we just integrated with respect to x. Then if we bring the e to the 2x to the right hand side, so this is going to be a of ye to the minus 2x. Then we're going to apply the given Cauchy data. So when x is 1/2, u is e to the y. So on the left hand side here we're going to have e to the y on the right hand side, we're going to plug in x is 1/2. If we do that, this term is going to be vanish actually. So we're going to have a of y e to the -1. So this is telling us that a of y is going to be e to the 1 plus y. And then if we plug this here, then we have our final solution. So u will be 1/4 2x minus 1 plus e to the power 1 plus y minus 2x. So that is going to be our final solution. In C, we have got a third order or PDE, but it's linear because it's just a third order derivative of u. So this one we can evaluate a bit similar to A by just integrating, but we're going to have to integrate repeatedly 3 times here. So if we integrate once with respect to y, then the left hand side is going to be uxy. On the right hand side, integral of 6y is going to be 3y squared. The x remains the same because we treat it like a constant. Then we're going to have to add a function of x. Then we integrate again with respect to y. 3y squared now becomes y cubed. Integral of this with respect to y is going to be f y times f of x. Then we are going to have to add another function, g of x. Then lastly, we integrate with respect to x. So this is going to be y cubed ln magnitude x plus y integral of f of x plus integral of g of x f g plus an arbitrary function of y. At this point, since we can do one of two things. We can either define these as new functions of x, or we can simply go to this step here, because we can see that we're going to integrate this and make these derivatives of f, and then this is simply going to be y f of x plus g of x plus h of y, and so that is going to be our general solution. Then in D, we have u y for u equals to 0 when y is equals to pi on 4, u is equal to e to the minus 2x, and then the y derivative of u when y is pi on 6 is equal to 0. Okay, so this is a boundary value problem. Now, since this is linear, so that's the first condition, and second, it's just derivatives of y. Okay, then we can treat this as an ODE. So the ODE would be look something like this, of which then the auxiliary equation would look something like that, from which r would be plus or minus I. So we're going to do the same thing here. Then the general solution of this is going to be not y but u. So it's going to be u of xy. So here the solution would be a cosine 2x plus b sine 2x, where a and b are arbitrary constants. Okay, well, in this case the solution is going to be a, but it's going to have to be a of x. So when you integrate partially, you get arbitrary functions as opposed to arbitrary constants. So this is going to be our general solution. Then we see here that we are going to need the y derivative before we plug in. So differentiate this. So it's going to be 2b cos 2y minus 2a sine 2y. So that's the y derivative. So when x is pi on 4, u is e to the minus 2x. So when we plug that one here, then this side we're plugging in x is pi on 4. So that's going to be ax cosine pi on 2. Sorry, that's b of x there. B of x sine pi on 2. Cosine pi on 2 is 0. So that means this vanishes. Sine pi on 2 is 1. So this is telling us that b of x is e to the minus 2x. Then when x is pi on 6, uy is 0. So we're going to plug in pi on 6 here. The left hand side is going to be 0. So we're going to have 2b. b is e to the minus 2x cosine pi on 3. We've already so this is going to be minus 2a sine pi on 3 sine pi on 3. Okay, so that means from here we can find a. I'm going to bring this to the right hand side, left hand side. So 2a sine pi on 3 is root 3 over 2. Cosine pi on 3 is 1/2 minus 2x 1/2 here. So this is telling us that a of x is going to be, this cancels out, that cancels out, 1 over root 3e to the minus 2x. Down. Okay, so I've got a and b, and therefore we can write the solution. So this is going to be e to the minus 2x over root 3 cosine 2y, e to the minus 2x sine 2y. So if you factor out e to the minus 2x, then this is 1 on root 3 cosine 2y plus sine 2y. Alright, so that sorts that one out. Then we're going to go to e. In e, we have got x uxy plus 2uy 2uy is equals to 2y. Now this PDE here is such that the y derivative can be factorized. So we could write this as partial y of xux plus 2u, because if you differentiate this with respect to y, you get this. It won't be a product because this is independent of y. And then once you've got it like this, it means the left hand side is an exact derivative which we can integrate, exact derivative of y. So if we integrate with respect to y, integral of 2y with respect to y is y squared, and then this is going to be plus a function of x. And then this now is a first order PDE with only one derivative, so we can treat it as an ODE, linear for that matter. So if we divide everything by x here, 2 over xu, y squared over x, 1 over x f of x, then we can integrate this. The integrating factor going to be the exponential with the integral of 2x dx. It's 2 over x dx, going to be x squared. So that means this left hand side, if we multiply everything by x squared, we can write it like this. This becomes xy squared x f of x. Then we can integrate this. So we're going to have x squared u, x squared over 2y squared. This is just going to be the integral of f of x, but then we have to add a function of y. Then we multiply everything by 1 over x squared. So this is going to be y squared over 2, 1 over x squared. This is x f of x dx, g of y over x. And then the middle term here is all just a function of x, so we can write that as h of x, g of x over x, and that's going to be our general solution. All right, at this point we're going to give you a few to try. You can just pause the video, have a go at these, and then when you continue the video, then you can scroll down to our answers. All right, so please do have a go at this one. So if we have got y uy equal to 2x, in G we have got ux minus square root u equal to 0. In H we have got uy minus 2yu equal to y. Then we've got Cauchy data here. When y is root 2, u is e to the 2x minus half. I, we've got uxxy equals sine 2x minus 3y. J, we've got 2uxx plus 3ux minus 2u equal to 0. We have got initial conditions here. When x is 0, u is e to the minus 2y, and then the x derivative is 0. And then for k, we've got y uxxy plus uxx equals to 0. Yeah, so please just have a go at those ones, and yeah, just press pause the video, and then when you continue, you can scroll down to our solutions. All right, we're now going to scroll down to our solutions. So for f, if we bring the y over to the right hand side, then the PDE looks like this. Then this we can simply integrate with respect to y, and so it's going to be 2x ln y plus a function of x. This one as first order is only derivative with respect to y. If we write it like this, we can separate variables just like in PDEs with variable separable feature. We bring all the u's this side and we integrate. So that's going to be the integral of this. This integrates to y as a function, an arbitrary function of x. Making u the subject of the formula gives us that as the solution. Here again, only derivative with respect to y. So we can treat this as an ODE. That's going to be the integrating factors of multiply both sides by e to the minus y squared. Then the PDE is going to look like this. This we can integrate. This we can integrate as well using u substitution. This is an arbitrary function of integration. So if make y the subject of the formula, the solution is going to look like that. Then if we apply this, then that means on this left hand side, we are going to have e to the x minus that, and on the right hand side we're plugging in y is root 2. So here the minus half is going to cancel out, and so this is going to be our a. If we plug it into this expression here, then our solution is going to look like that. Okay, part I is just one derivative, but it's third order, so we're just going to integrate 3 times. So integrate once with respect to y. Just make sure that you get the signs for the integrals here. So we're going to divide by 3. Integral of sine is minus sine, but this is negative, so 2 negatives is going to make a positive. So integrate again. This is going to be, so this I made it f double prime because I can see here which is going to integrate twice with respect to x. So integrate this, it becomes f prime, but there's going to be a function of y integrating this gives that, and then integrate again, and that's our final solution. Here we have got in J only derivatives with respect to x, so we can treat this like this second order linear ODE. The roots of this are going to be 1/2 and minus 2. So the solution is going to look like this. Looking at the boundary conditions, we see that we're going to need the x derivative. So we're going to differentiate this with respect to x. So that's going to be the derivative there. Then if you apply these two boundary conditions, we find that a plus b must be equal to e to the minus 2y. A over 2 minus 2b is going to be 0. So this gives us a is 4 over 5 e to the minus 2y, b is e to the minus 2y over 5. So the solution is going to look like that. Here we have got two x derivatives here. This is a y, so we can integrate this with respect to x twice, which we do here first and then second, and then this is now a first order ODE because there's only one derivative, and in fact this happens to be an exact derivative, so just write it as partial of y yu, and then integrate. When you divide by y here, this is going to be a function of y, which you call it big F, and that's a function of y, and that's going to be h over y. Okay, thank you. Hopefully this has been useful. You if it does help, please do subscribe to our channel so that you can get notified whenever we post new stuff. Thank you.